In this video, we will see the concept of branch and bound algorithms. A branch and bound algorithm consists of a systematic enumeration of candidate solutions by means of state space search. And the set of candidate solutions is thought of forming a rooted tree with the full set at the root. That means that we will be enumerating all the possibilities that may lead to the solution in the form of a tree, and we will search for the optimal solution in that tree. We can see that all the possible options of the solution is forming a rooted tree with full set of the possibilities at the root. Okay. The algorithm explores the branches of this tree, which represents subsets of the solution set, which means that the branches of the tree will be representing the subsets of the solution set. And this is the important point. Before enumerating the candidate solutions for a branch, the branch is checked against upper or lower estimated bounds on the optimal solution and is discarded if it cannot produce a better solution than the best one found so far by the algorithm. Which means that whenever we do the state space search, we do not have to check each and every node one by one. The choice of choosing a node at a particular stage is determined by this upper or lower bound, which means that we will have a method by which we would have found an upper bound for a branch. So that value of upper bound decides whether we have to choose that branch or not. The criterion that decides whether to choose a branch or not is dependent on the value of upper or lower bound. A branch is selected if the benefit that we can get by selecting a branch is better than the upper bound that we have already found so far. One example problem which uses the concept of branch and bound algorithm is the 0-1 knapsack problem. We will go through the 0-1 knapsack problem in detail, so you will get a better picture of the points that I have listed over here. The problem statement for the 0-1 knapsack problem goes like this. You have several objects and each of those objects has a weight, let's say W1, W2, W3, etc. up to Wn. Okay. So this is my W or the weight array. Each of those item or each of those object has an associated profit. So let's say P1, P2, P3, etc. up to Pn. Okay, so you can also have the indices starting from 0 through n-1. That doesn't matter. And then you will have a knapsack or a bag in which you have to carry these items such that you will have to get maximum profit, provided that this knapsack has a limit on the weight that it can be carried equal to m. Okay. The aim is you have to carry objects which give us the maximum profit. At the same time, the total weight of the objects that we have selected should not exceed the capacity of the knapsack. Okay. Your job is to select some objects from the given objects such that you will be maximizing the profit. At the same time, the total weights of the objects that you have selected should not exceed the knapsack's capacity m. Okay. And we will see how this problem can be tackled using the branch and bound approach. Let's say you are given a set of profits where you have the values like 45, 30, 45, 10, and you have the associated weights of those objects as 3, 5, 9, 5. Okay, we have in total 4 objects, so the number of objects is 4, and the capacity of the knapsack is given as m is equal to 16. So our aim is to select objects from these 4 objects such that the total weight of the objects that we have selected should not exceed 16, and at the same time you should get the maximum profit as possible. So one straight way of solving this one is by using a greedy approach. I will show that greedy approach, and that will be helpful for us to calculate the bounds that we have mentioned previously. One criteria for choosing an object is looking at its profit to weight ratio. That is the ratio P to W. That means which gives the maximum profit for a unit weight. So if you divide the profit with its corresponding weights, then you will get a new set as 45 by 3 is 15, 30 by 5 is 6, 45 by 9 is 5, 10 by 5 is 2. Okay, this indicates that if you carry 1 kilogram of the first object, you will get a profit of 15. You should first select the object which has the highest profit weight ratio as much as you can. Then you go for the next object which has the next highest value of profit to weight ratio, and so on. This is the greedy approach that I have mentioned. So these numbers give us a criteria for choosing each of the objects from the given objects. If I select the first object completely, knapsack has got an object of weight 3. So the total weight of the knapsack by far is 3. Okay. Then I will be choosing for the second object. The second object has a weight of 5. So I'm choosing that 5. So the total weight is now 8. Then I can go for selecting the third object because it has the next highest profit to weight ratio. So I'll be selecting the object, so it has a weight of 9. So the total weight will be now 8 plus 9, which is equal to 17. So you can see that that is now a violation of knapsack capacity. So if you are going for a greedy approach and if you are going for a fractional knapsack problem, then you are allowed to take the fractions of weights of those objects. If that is allowed, you can select 3 kg of the first object, then 5 kg of the second object, and as the third one you have the maximum capacity equal to 16. So here we have already selected a weight of 8, so you can select 8 kg of the third object as the next item to fill into the knapsack. So this weight is now 16. If this is the case, then you can calculate the total profit as, if you select 3 kg of the first object, then you will get a profit of 45, plus if you select 5 kg of the second object, you will get a profit of 30. If you select 8 kg of the third object, you will have a maximum profit of, so this is the profit per kilogram. So if you are selecting 8 kg, then it will be 8 into 5. So this will be equal to 45 plus 30 plus 40, which will be equal to 115. Okay, and this is the maximum profit that we can have if we are allowed to take a fraction of an object. But in 0-1 knapsack problem, we are not allowed to take a fraction of an object. In that, we can either choose an object completely or we cannot choose that object at all. In 0-1 knapsack problem, we will be utilizing the result of fractional knapsack problem in order to get the value of the upper bound. In 0-1 knapsack problem, we will be using the profit of the fractional knapsack problem as the upper bound in order to select a branch in the state space tree. Now let's look at the 0-1 knapsack problem. We are given with 4 different objects, x1, x2, x3 and x4. All of them have an associated weight p is equal to 45, 30, 45 and 10, and the associated weights. And the ratio of the profit to weight is given here. We will be utilizing this value in order to calculate the upper bound using the fractional knapsack approach. And the capacity of the knapsack is given as 16. And if I am not selecting an object, I will be indicating it with 0. And if it is selected, I will be indicating it with 1 in the state space search tree. So we are starting our problem with an empty knapsack. So I will have a total profit equal to 0, total weight equal to 0, and we have to calculate the upper bound. We will be utilizing the fractional knapsack approach to calculate the upper bound. So I am selecting the first object entirely, that is x1, because it has the highest profit to weight ratio. So I am selecting x1, so the weight of x1 is 3, and I am selecting x2, the weight of x2 is 5. So we have a total weight of 8 kg now. We can accommodate another 8 kg in order to make the weight of the objects equal to 16, which is equal to the capacity of my knapsack. So in order to do that, I am selecting x3. The complete weight of x3 is 9, so I will not be selecting the complete weight. I will be selecting only 8 kg of x3. So we have these weights. So these weights will be in total equal to 16, and the corresponding profit will be for 3 kg of x1, the profit is 45. For 5 kg of x2, the profit is 30. And for 8 kg of x3, the profit per kilogram is 5. So I am multiplying 5 into the weight I am choosing is 8. So this will be in total 115. So this is my upper bound. That is, this is the maximum possible profit I can obtain from this problem if at all I am choosing a fractional knapsack approach. So this is 115. Alright. Now we are starting selecting objects. So to begin with, I have two options with x1. I can either choose x1 completely or not choose it at all. So I'm drawing those possibilities here. So I have two options, either select x1 completely, that is x1 equal to 1, or not select x1 at all, that is x1 equal to 0. If I select x1, the profit is 45, and the weight that will be added to my knapsack will be 3. Now we have to calculate the upper bound. By selecting x1, we saw that I can have a maximum profit of 115. So the maximum upper bound is 115, And if you do not select x1, so we haven't earned any profit so far, we haven't added anything to my knapsack. Now the value of upper bound has to be calculated by avoiding the value of x1. So I'm not choosing x1, I can choose x2. The complete weight of x2 is 5. I can select x3 also. The complete weight of x3 is 9. So we already had 5 plus 9 equal to 14. So we can accommodate 2 more kilograms. So we will be accommodating 2 kilograms of x4. So this will add up to a total weight equal to 16. The corresponding profit will be 30 plus 45 plus 2 kilograms of x4. 1 kilogram has a profit of 2. So 2 kilogram will be 2 into 2, which will be equal to 30 plus 45, 75. 75 plus 4 equal to 79. So the upper bound of this node will be 79. Okay. Now we have two nodes to choose from. One has an upper bound equal to 115, the other one has an upper bound equal to 79, and we will be choosing a branch which will give us the highest value of upper bound. So we will select this one. From this point I again have two options. I have already selected x1. Now I can select or not select x2. Now I have one branch that indicates I have selected x2, that is x2 equal to 1, or otherwise I have not selected x2, that is x2 equal to 0. If I select x2, the maximum profit I can achieve is 45 plus 30, that is equal to 75, and the total weight that I can add into my knapsack will be 3 plus 5, which is equal to 8. Now the upper bound will be again 115 because we have selected x1 and x2. Those options were also selected when we calculated an upper bound of 115. So the upper bound is 115. If you do not add x2 into the knapsack, then the total profit will be again 45. The weight will be 3, and we had to recalculate upper bound because we are not choosing x2. So we have selected x1. So the x1 has a total weight of 3. We are not selecting x2, so I have a chance of selecting x3. x3 has a total weight of 9. So in total this has weight equal to 3 plus 9, which is equal to 12. Now I can add 4 kilograms more into my knapsack. So I'm selecting the object x4. x4 has a total weight of 5, so I will be able to add only 4 kilograms. So in total this will be equal to 16, and the corresponding profit values will be 45 plus 45 plus 2 into 4, that is equal to 98. So this is the upper bound of this node. Now presently we have 3 different nodes to start the next branch from, but we will be going for the one which has the highest upper bound. So the values of upper bounds that we have now is 115, 98 and 79. So we will select this node to start the next branch from. So in the next step I have two different possibilities. That is, I can either select x3, that is x3 equal to 1, or not select x3 at all, or x3 equal to 0. If I select x3 completely, if you calculate the weight will be 3 plus 5 plus 9, which will be equal to 17. So we cannot accept this possibility. So we cannot select x3 because this is violating the capacity of the knapsack. Now we will examine the option of not selecting x3. So the profit will be again 75. The weight will be 8. Now we have to recalculate the upper bound because this upper bound 115 was calculated by taking a fraction of x3, but now we are not choosing x3 at all, so we have to recalculate the upper bound. So we have selected x1 with a weight of 3, we have selected x2 with a weight of 5, and we are not choosing x3, we are going for x4. Now we have is 3 plus 5, which is equal to 8. So we can add 8 more kilograms of the next object, but the last object has only weight of 5, so we are choosing it completely. So this has a total weight equal to 13, so which is inside the capacity of my knapsack. Now the profit of this selection will be for 3 kilograms of x1 we have a profit of 45. For 5 kilograms of x2 we have a profit of 30. For 5 kilograms of x4 we have a profit of 10. So this will be equal to 45 plus 30 plus 10, which will be equal to 85. So the upper bound of this particular node will be 85. So we have the upper bounds 85, 98 and 79, and we will be choosing the one which has the highest upper bound, that is equal to 98. So we will start our next branches from this particular node. We reached this node by selecting x1 and not selecting x2 at all. Now we have an option of either selecting x3 or not selecting it at all. Now I will draw those possibilities. That is, I have two different branches. The first one is for x3 equal to 1 and the other one is for x3 equal to 0. And if I select x1 and not selecting x2, then selecting x3, the profit that I am going to get is 45 plus 45, that is equal to 90. And the weight will be 3 plus 9, that is equal to 12. The upper bound will be 98 again, because we calculated this upper bound by avoiding x2 and including x3 and x4. So we can write the upper bound equal to 98. Now for this one, if you are not choosing x3 at all, then the profit will be again 45, because that is the profit of choosing only x1. Then the weight will be again 3 and the upper bound has to be recalculated. For this node we are choosing x1, so the weight of x1 is 3. We are not choosing x2, we are not choosing x3, so we can choose x4. So x4 has a weight of 5. The total weight is 3 plus 5 equal to 8, and the total profit will be 45 plus 10 equal to 55. Now we have 4 different nodes where we can start the next branch from. We have this node where we have an upper bound of 85. Here we have an upper bound of 98. Here we have an upper bound of 55. Here we have an upper bound of 79. So we will choose this node to start our next branch from, because this has a guarantee that the upper bound is 98 and all other nodes has an upper bound which is less than this value. Now from this point onwards, I have two different options, that is I am choosing x4 or I am not choosing x4 at all. So I am drawing those possibilities over here. That is x4 equal to 1 or x4 equal to 0. And if I select x4, that is I am selecting x1 and not selecting x2, selecting x3 and selecting x4. So the total weight will be 3 plus 9 plus 5, and this will have a weight equal to 17. So we cannot choose this node because that will exceed the capacity of my knapsack. By not choosing x4, the profit that I will earn will be the profit from x1 and x3 alone. The profit of x1 is 45 and the profit of x3 is 45. So the total profit is 90. The total weight that I have is 3 plus 9 equal to 12. And the upper bound is we are selecting x1, we are not selecting x2, we are selecting x3 and we are not selecting x4. The total weight of x1 is 3, the total weight of x3 is 9. This has a total weight equal to 12, and the maximum profit that I can earn from this combination will be, even if I choose the fractional approach, then it will be 45 plus 45, which is equal to 90. So the upper bound of this node is 90. Okay, now if you look at all the nodes which we can have the next branch from, this is one node and this is another node, this is another node and this is another node. And out of these 4 nodes, the upper bound of this node is 90 and all other nodes has an upper bound which is less than this node. So there is no point in looking at these 3 nodes because it will have a maximum value of the profit equal to 85, 55 and 79 respectively. But we have already achieved a profit equal to 90. So we will not be looking at these possibilities. So we will fix that this is our final solution. Okay, so this is our final solution. We do not need to look at these 3 nodes. Okay, so our final solution set will contain only x1 and x3 alone, and the weight will be 12 and the profit that I'm getting is 90. Okay, so this is our final solution. If you look at this tree, you can see that we have reduced the number of search possibilities from this tree into this tree. That is, we have reduced the number of ways that we have to search. So this is an efficient way of enumerating the possible solutions rather than completely enumerating all the possibilities or a brute force approach. When you look at this diagram, you can see that we are branching the next possibility only depending on the value of the upper bound. So that is why this is known as a branch and bound algorithm. I hope the idea is clear. Thank you.